Okay, guys, welcome to Physics 390 Class 6. This is on the TISE, or time-independent Schrödinger equation for the free particle, and this covers Chapter 2.4 of our textbook. So the TISE for the free particle gives rise to stationary states, just like the harmonic oscillator and the infinite square well did. So let's see what these might look like. So for the free particle, the potential is equal to 0, just like in the interior of the infinite square well. Remember, in the infinite square well, there was no force, and the free particle means no force. So we represent that by the potential being 0. So our TISE becomes the kinetic energy term minus h bar squared over 2m second derivative. There's no potential energy term because that's 0 is equal to E psi. And then we can do the same substitution as we did for the infinite square well inside the infinite square well, where we let k be the square root of 2me over h bar. And then multiplying through on this equation, we get the second derivative is minus 2me over h bar squared psi, which would be minus k squared psi. And that puts this equation in a form that we recognize. It's a harmonic form, just like the classical harmonic oscillator, but with different variables. So the solutions to this, if you remember, for the infinite square well, were sines and cosines. That's a harmonic solution. Here, because there's no boundary conditions, in the infinite square well, there are boundary conditions at 0 and a. So that made the cosine and sine more convenient. But here we can write the harmonic solutions. It's more convenient, it turns out, to write them as e to the I kx and e to the minus I kx. So complex exponentials. And these are related to the cosine and the sine through Euler's identity, that e to the I theta is cosine theta plus I sine theta. So these are really harmonic solutions, just a different way of expressing them. Okay, so this is just a function of x. We know that stationary states the wave functions do evolve in time. So we insert the exponential time dependence, e to the minus I e t over h bar, to each of these states, using e equals h bar squared k squared over 2m, okay, which we can get by solving our definition of k up here for e. If we square both sides, we get k squared equal 2me over h bar squared. So e would be h bar squared k squared over 2m. Okay, so we put that in here. And so we put e to the I kx times e to the minus IE t over h bar, plugging in h bar squared k squared over 2m for e. So dividing that e by h bar, we get h bar k squared over 2m, which is what we have here. We factored out a k, so it's h bar k over 2m times k, which is h bar k squared over 2m. And likewise over here, we have minus I kx. And then since this minus is out in front, this distributes in, and we have the e to the minus I k h bar k squared over 2mt. So we have the same exponential factor, time exponential factor on both of them. So these two terms are traveling waves because they're of the form x minus some number times t. Any function x minus some number times t is a traveling wave where the velocity is that number. And this x plus some number times t would be a traveling wave moving to the in the opposite direction, in this case to the left, assuming k is positive. So it can be useful to write these sort of in a unified way as just these two together as just psi k is the first, similar to the first term, but letting k be either positive or negative. Okay, so if k is negative, it looks like the second term because it'll be a e to the minus I kx. If k is negative, this I kx will be negative, just like it is here. And that would represent moving to the left. Whereas if k is positive, it represents moving to the right. So we can represent both of these with just a single equation or a single representation where k can be positive or negative. Okay, so what about the wave speed? We said it's a traveling wave. Well, to get the wave speed, we divide the coefficient of t by the coefficient of x. That gives the wave speed. And here that would turn out to be the wave velocity would be h bar k squared over 2m over k, or h bar k over 2m. The wave speed would just be h bar, since k can be positive or negative, h bar absolute value of k over 2m. And then that can be written in this form, square root of e over 2m. All right, so to see that, if we come up here to this definition, if we multiply through by h bar, we have h bar k equals square root of 2me. If we divide by 2m, we have h bar k over 2m, but then this square root of 2me gets divided by 2m, so it becomes square root of e over square root of 2m, which is what we have here. So it's just another way, square root of e over 2m is just another way of using this definition here, another way of rewriting h bar k over 2m. Okay, so it seems like we're doing well. We've got these stationary states, they're moving along. So let's see if there's any issues. It turns out there are two issues with these stationary states. Psi k equals e to the I kx minus this quantity. The first issue is an inconsistency between the quantum and the classical speeds. So the quantum speed was just found to be v quantum is square root of e over 2m. We just found that on the previous slide. The classical speed for the particle with a kinetic energy E and a mass m would come from the classical ke equals 1/2 mv squared. So that would be, we would multiply through by 2, divide by m, and take the square root. And so we'd get v classical would be the square root of 2e over m. But if you compare these two, you can see that this one is greater. And in fact, to get from the top one to the bottom one, you'd have to multiply by 2, because 2 over the square root of 2 is 2 over the square root of 2 is the square root of 2. So the classical speed is twice the speed of the quantum stationary state. So the quantum wave function or stationary state travels at half the expected speed, okay? So that seems to be a problem, a sort of a mismatch between the speed that we expect for a kinetic energy, a particle with kinetic energy E, and the actual speed we get for the stationary state here. And we'll see that we can resolve that, and we'll resolve that later in this video. The second problem is we know that all wave functions or stationary states have to be normalizable. So if we look at this function here, if we take the normalization integral from minus infinity to infinity, we're going to get the complex conjugate times the psi k back again. If we take the complex conjugate, we just put a minus I becomes minus I. If we multiply that by this back again, this e to the minus I times all this cancels e to the I times all this, and we just get a squared. The e to the minus I and the e to the plus I cancel. So therefore, we can pull out the a squared, and we're left with just the integral from minus infinity to infinity of 1 dx. But that diverges because 1, if you integrate 1 from minus infinity to infinity, that's infinity. So there's no value of a that we can choose to make this integral equal to 1. It's an infinite integral. So we can conclude that these stationary states, although they satisfy the time-independent Schrodinger equation, they don't represent physically realizable states because they're not normalizable. So we can say there's no such thing as a quantum-free particle with a definite energy. That is one particular energy. There's always a spread of, as we'll see, a spread of momenta and energy in the normalizable states. Okay, so let's take a look at these two issues and how we might resolve them. Resolving issue 1, we introduced the concept of a wave packet and also the mathematical idea of a Fourier transform. We can create a linear combination of stationary states, these harmonic stationary states, which is normalizable, called a wave packet. Okay, and this is a picture of a wave packet. You can see it does oscillate like the harmonic stationary state, but it doesn't continue indefinitely to infinity on either side. It just goes up and gradually its amplitude decreases. So it can be normalized because it doesn't just continue indefinitely with a non-decreasing amplitude. And we can, it's the linearity property of the Schrodinger equation that allows us to combine all these stationary states together and still get a solution. So we can add in any way we want all these stationary states that we found, these harmonic stationary states. Any linear combination of them is also a solution. So this wave packet is guaranteed to be a solution if it's made up of the harmonic stationary states. Okay, so what does that look like? So this is the what it would look like. So we would have the wave function at x and t would be our stationary state with the time dependence in, which is what we're looking at on the first slide, weighted with a by phi k, which is a weight we give to each of these stationary states. And then we weight each of them by a certain phi k, and this factor of 1 over square root of 2 pi is just here to make the formulas come out a little bit neater, as you'll see in a second. But we weight it by phi k, and then we add them all up. So phi k tells us how much weight we put on a given stationary state with wave number k. Okay, so so the question becomes, how the heck do we determine this function phi k? We may have a particular wave packet in mind, but how do we determine how to create it? What component, what stationary states and what weight should they have to create a given profile of our initial wave packet? So how do we determine the function phi k, which produces the initial wave packet in the equation psi of x0 is 1 over square root of 2 pi integral from minus pi infinity to infinity phi k e to the I kx dx. And this equation here is this equation up here just with t equals 0 plugged in. So with t equals 0 plugged in, this term disappears, and we just under the integral we get phi k e to the I kx. So so in this equation, psi x of 0 is called the Fourier transform of phi k. Okay, that's just a definition. And it's the continuous version of a Fourier series. So in a Fourier series, we take sines and cosines, and we add up an infinite number of them, but a a discrete infinity. So its index n equals 0, 1, 2, 3, 4, 5, and so forth. Whereas and that Fourier series is only defined on a finite interval. And then it repeats outside that interval because it has a discrete infinity of components to it. N equals 0, 1, 2, 3, and so forth. In the Fourier transform, we have a continuous range of stationary states with wave number k, and we integrate over that continuous range. So it's a full continuous infinity, not a discrete infinite sum. It's a continuous continuous integral over all of these k. So that's the Fourier transform. And then there's a really neat property of Fourier transforms, which is the inverse Fourier transform has almost the same formula as the Fourier transform. So if we have psi of x and 0 as the Fourier transform of phi k, we can get phi k using the inverse Fourier transform. And phi k turns out to be 1 over square root of 2 pi, integral from minus infinity to infinity, psi of x and 0, e to the minus I kx dx. So if you compare these two formulas, the difference between them is that we've switched phi k and psi x0 because we're looking for phi k here. And the other difference is that we have e to the I kx here, whereas here we have e to the minus I kx. Okay? So these are the Fourier transform and the inverse Fourier transform. So if we're given an initial wave packet at time 0, psi x of 0, we can take the inverse Fourier transform of it. We get phi k, and then we can take that phi k and put it back in this initial equation we have, the first equation, and we have psi of x and t. So we take the initial wave function, we take the inverse Fourier transform of it to get the weights of all the stationary states, and then we put that back into the expression for psi x and t. Okay. So that's kind of the way we build up a wave packet at time t. All right, so let's do an example of that so we can visualize this a little bit. There's a lot of integrals and mathematics there. So suppose a free particle has an initial wave function given by psi of x of 0 is some constant capital A between minus lowercase a to positive lowercase a, and it's 0 otherwise. Okay, and that's pictured here. So between minus a and a, psi x of 0 has a given value, and outside it's 0. So this is an initial wave function which is localized around x equals 0. If we normalize this, it turns out that this constant a must be 1 over the square root of 2a. And that makes sense because if we integrate psi x0 squared, we're going to get a squared from minus a to a. So if we take a squared, that's 1 over 2a. And if we integrate from minus a to a, that's a length of 2a. So it'd be 1 over 2a times the length of 2a, which would give 1. So the normalization factor the factor a can be determined to be 1 over the square root of 2a, which is shown in this picture here. The amplitude here is 1 over the square root of 2a. Okay, so we have the initial wave function. We can find the phi of k to represent it as a superposition of stationary states using this expression here, the Fourier transform. So we have phi k is 1 over the square root of 2 pi, integral from minus infinity to infinity, psi x of 0, e to the minus I kx dx. I'm sorry, that's actually the inverse Fourier transform. I might have said the Fourier transform. This is the inverse Fourier transform because it's got the e to the minus ikx here. So plugging in for psi x of 0, which is 1 over the square root of 2a between minus a and 0 outside, we can simplify this integral. So it looks like this. We have the 1 over square root of 2 pi coming down, and then the integral from minus infinity to infinity, since psi is 0 outside minus a to a, the limits of integration just become minus a to a. And then we bring out the 1 over the square root of 2a for the wave function. And then we're left with the integral from minus a to a of e to the minus ikx. Okay, and so combining some terms here, we can do that integral. We just use the power rule, and we get that integral, and we go through the steps here, evaluate it from a to minus a, and we get this expression here, involving the exponential e to the ika minus e to the minus ika over 2I. And that can be shown to be equal to sine of Ka, okay, using Euler's identity. So our overall phi k, the weighting of these stationary states, will be 1 over square root of pi a times sine of Ka from this factor over k. Okay, so that's our inverse Fourier transform, which gives us our weighting of the stationary states. And that looks like this. It's harmonic. It oscillates because we have sine of Ka, but so this is a plot of k on the x-axis and phi of k on the y-axis. So it's harmonic, it oscillates, but as k increases in either direction, the amplitude decreases. So as k gets bigger and bigger, this denominator gets bigger and bigger, and phi of k gets smaller and smaller. So it falls off eventually. But you can see that to produce this localized wave packet, the square wave packet, we have to introduce a range of k values. Okay, a range of k values, weighting at different k values, including positive and negative k values. Okay, so all right, so given this phi of k, we can construct the full solution. As we talked about the procedure, which we talked about more abstractly on the previous slide. So the full solution, psi of x and t, is 1 of the square root of 2 pi, the integral of phi of k times this stationary state evolving in time. So we can just plug in the phi k, which is here 1 over the square root of pi a sine of k over k. And let's see, moving this square root of pi a out in front, we get 1 over the pi square root of 2a times sine of ka over k in the integral times this exponential factor. Okay, so this would be our final solution, and it's a closed form solution, but we can't integrate this. It doesn't have an antiderivative, so it has to be evaluated actually numerically to plot it. But that's been done, and I'm taking this from the textbook. But let's take a look at what happens as time progresses, as t goes from 0 to some small t. At t equals 0, we should recover the initial wave packet, which we do. It's this square guy. Okay, so that's t equals 0. As time progresses, the wave packet gradually spreads out. Okay, so it starts to spread out from its initial concentrated form. And the reason it spreads in time is because the range of k implies a range of momentum p, because p is h bar k. So, and a range of momentum means a range of velocities. So all these component velocities, some of them will be large and positive, some large and negative, some close to 0. So part of the wave will move to the right very quickly, part of the wave will move to the left very quickly, and part of it will not move much. And so that has the effect of making this wave packet spread out in time, okay, spread out from its initial packet. And that's called wave packet spreading. And it's a general feature of wave packets that they spread out in time because of the range of wave numbers k and the range of momenta p and velocities v that they have. Okay, so that's a worked example of a wave packet, and you can see the wave packet spreading pretty clearly in this figure. Okay, all right, so let's go to issue 2. To resolve issue 2, which was that the velocity of the stationary state was half what we expected, we have to learn to distinguish between something called phase velocity and group velocity. And this is common to all waves, not just wave functions. Water waves, waves on a string, and so forth. So the component waves in a wave packet each travel, the stationary states each travel at their own phase velocity, which we call Vp for phase, while the wave packet envelope, so if we add up all these waves together, if we trace out the envelope of the sum of them, that envelope moves along with what's called the group velocity Vg. So you can see that in this picture where the envelope here is moving with Vg, while the individual wave is moving, one of these individual waves here is moving with Vp, the phase velocity. And depending on the type of wave, the group velocity can be less than, equal to, or greater than the average phase velocity of the waves making up the group. So let's see what it works out to be for this, the free particle, the quantum free particle. So assuming that our phi of k, our distribution of wave numbers making up our wave packet, is fairly narrowly peaked around a particular wave number. And that will make the, if it's fairly narrowly peaked, that will make the spreading fairly slow. So we have a well-defined wave packet for at least some time, and we can measure its group velocity meaningfully, the envelope velocity. If phi of k is not that narrowly peaked, if it's very spread, there's going to be so many different velocities that it'll just spread very quickly, and we can't define the group velocity very well. So assuming that phi of k is narrowly peaked, it can be shown, and you can see the textbook for the derivation of this, that the phase velocity is omega over k, which you may recognize as a formula for the velocity of a wave with angular frequency omega and wave number k. And the group velocity turns out to be the derivative of omega over k, where omega is thought of as a function of k. And both of these would be evaluated at k equal k0, where the wave packet is, the wave numbers are concentrated. So what we call the dispersion relation is the relationship between omega and k. And here that dispersion relation is omega is h bar k squared over 2m. And this is familiar from the earlier where we had omega being h bar k squared over 2m. But if you ever forget it, you can think, well, if I multiply the left and the right side by h bar, I get h bar omega, which is E, is equal to h bar squared k squared over 2m, which is p squared over 2m. So this is really another way to write E equals p squared over 2m. Okay, so that's our dispersion relation for the quantum free particle. So if we take this definition of the phase velocity and divide by k, we get h bar k over 2m, just dividing k squared by k, h bar k over 2m. On the other hand, if we take the group velocity, we're going to differentiate omega with respect to k, and we get, so if we differentiate, we get h bar times 2k over 2m. So the 2's cancel, and we get h bar k over m. So you can see that the the group velocity is twice as big as the phase velocity. So the group velocity, as I said, is twice the phase velocity. And so the group velocity matches, because before the phase velocity, which we had, was 2 times too small, smaller than the classical velocity of the particle that we expected. But the group velocity is twice as big, so it exactly matches the expected velocity of the particle that's being represented. Okay, so this using the group velocity for the wave packet resolves the issue 2, that the apparent quantum velocity was too small by a factor of 2. Okay, so just to sum up real quick, we've seen that we can take the free particle, we can get stationary states, which are exponentials, complex exponentials. We see that there are 2 issues with them. One, that their phase velocity is a factor of 2 too small, and 2, that they're not normalizable. We can kind of take care of both of them really by adding up these stationary states with different weights and creating wave packets, which are localized waves which can be normalized. And then the group velocity of these wave packets, as defined as the derivative of omega with respect to k, turns out to give the expected velocities for the free particle. Okay, so the physical solutions that we think of to represent particles are these wave packets, these localized wave packets, which have a spread in position, because they're spread out in position, and also a spread in k, and so in momentum. And it turns out that spread in position times that spread in momentum, delta x delta p, has to obey the Heisenberg uncertainty principle, greater than or equal to h bar over 2. Okay? All right, thank you for your attention, and I will see you in class.